So in this video, what I want to do is to show that the rectangle, which has the maximum perimeter, which can be inscribed in a circle, is a square. So this is an example of a maximization problem where we're going to be looking at the derivatives. So if you have a problem like this, phrased in this way, I think it's extremely logical to start it by drawing a picture. And I've actually done this here already. So I've drawn Cartesian axes and I've drawn a circle which is centered at the origin. So the question is true for any circle, but we're not going to change the problem by not having the circle centered at the origin, and we make the problem much simpler by centering our circle at the origin. We then draw our rectangle, and again it makes life simpler for us, much simpler, if we draw the sides of the rectangle parallel to the y-axis and parallel to the x-axis. And I've said here that the radius of our circle is r, and I'm going to be looking at a general rectangle, so let me now give some names to the variables. So I'm going to say that this distance across the rectangle is 2a, so that means that I'm going from minus a here to a here, and similarly I'm going to go from minus b down here to b here. So I'm not assuming that they are the same, and what we want to do is we want to now work out what the perimeter is and show that we maximize the perimeter for this rectangle inscribed inside our circle by finding that a and b are the same. So that's what we're going to have to do. So we're going to need what the perimeter is, and the perimeter as a function of a and b is going to be 4a plus 4b. And the reason is that going from here to here, we're going from minus b to b, so this length is 2b, this length is also 2b, this length is 2a, this length is 2a, so all in all we get 4a plus 4b for the perimeter of our rectangle. And now what we want to do is to maximize it. So I'm going to make myself some more room by going on to the next slide. So to continue, all I've done here is I've drawn our graph again, a circle centered at the origin of radius r, and I've put in a rectangle here of width 2a and height 2b. And that means that the coordinates of the point up here in the corner, say, is going to be the x coordinate is a and the y coordinate is b. And our perimeter, as I have said, is 4 times a plus 4 times b. Now this looks as though it is a problem with two variables, a and b. But actually a and b are related, and there are many problems like this in calculus. So what we realize is that because this point AB lies on our circle of radius r, these coordinates a and b must fulfill the equation of a circle. So let's recall the equation of a circle, and on a circle the points have to fulfill the equation if it's centered at the origin. X squared plus y squared is equal to r squared. So this means for our particular point AB that a squared plus b squared is r squared, so therefore b is going to be the square root of r squared minus a squared. And I've chosen here the positive root because I've said that this is b, and b is therefore clearly positive, so it's safe to take the positive root here. So this means that we can write our perimeter as a function of one variable. Our perimeter We can write it as a function of a or b. I'm choosing to write it as a function of a. The first term is 4a, that's this term here. And then we have 4b, but we've just seen how to write b in terms of a. So this is plus 4 times the square root of r squared minus a squared. And this is the key result which we're now going to use. Having written the perimeter as a function of one variable, we're going to use this result and we want to maximize it. So that means that we want to differentiate this with respect to a and look for a stationary point. So we now look for a stationary point. So what I'm going to do on the next slide is just write out this equation again for the perimeter purely in terms of a, and I'm going to differentiate it with respect to a and see at what value of a we have a stationary point. So let's move on to the next slide. So the result that we had a moment ago was that the perimeter written in terms of one variable a can be written as 4 times a plus 4 times the square root of r squared minus a squared, because our other variable b we've seen can be written as the square root of r squared minus a squared. So we want to look for a stationary point, so we want the derivative with respect to a of our perimeter to be equal to 0. So let's start off by calculating the derivative with respect to a of our perimeter. So that means that we want the derivative with respect to a of 4a plus 4 times the square root of r squared minus a squared. The first term is rather easy. The derivative of 4a with respect to a is just going to be 4. In the second term, we can pull the 4 through the derivative, so we're going to get a factor of 4. We then realise that what we have here is r squared minus a squared all to the power of a half. So using the chain rule for powers, we bring a half down, and we then have r squared minus a squared all to the power of minus a half, and we multiply this by the derivative with respect to a of what was in the brackets, which is r squared minus a squared. So on the next line, this says that we have 4, and the next term is going to give us plus 2, and then r squared minus a squared to the minus a half is 1 over, so I'll just put it immediately on the bottom, the square root of r squared minus a squared. And then the derivative with respect to a of r squared minus a squared is going to be 0 from the first term minus 2a. So therefore, tidying this up, we have 4 minus, putting the minus sign out front, 2 times 2 is 4a, over the square root of r squared minus a squared. So therefore, this is, just to remind ourselves, the derivative of the perimeter with respect to a for whatever value a is. Now, at a stationary point, we want this derivative to vanish. So we want the derivative of this to be equal to 0, and if this is equal to 0, it must mean that 4 is equal to 4a over the square root of r squared minus a squared. So I write that out. I'm going to swap the ordering round. We have 4a over the square root of r squared minus a squared is equal to 4. So at that stage we realise that we can immediately cancel the 4's, and we will be left on the right hand side just with a factor of 1. And we can then multiply both sides by the square root that was on the bottom, and we obtain that a is equal to the square root of r squared minus a squared. And we recall now, as we've written here at the very beginning of this slide, that the square root of r squared minus a squared is b. You might want to go back and look at the previous slide. So this is equal to b. And if a is equal to b, this tells us that we have a square. So i.e. a square. So what I'd like to do on the next slide is to actually show that this is a maximum by calculating a second derivative. But let's just notice here that the important equations that we're going to need are our equation for the perimeter as a function of a, and also the first derivative, because to show that this is a maximum I'm going to calculate a second derivative. So I'll write out this equation and this equation at the start of the next slide. So up to now what we have seen is the following. The perimeter as a function of one variable a can be written as 4a plus 4 times the square root of r squared minus a squared, where the square root of r squared minus a squared is what we call b in our original diagram. The result that we've obtained for the first derivative is this, and we have seen that the first derivative vanishes when a is equal to the square root of r squared minus a squared. And what we now want to calculate is the second derivative. So we now want to find the second derivative with respect to a of the perimeter. And that, of course, is nothing but the derivative of the first derivative of the perimeter. So in other words, we need to calculate the derivative of 4 minus 4a over the square root of r squared minus a squared. Now, differentiating the first term is easy. It's a constant. We'll get 0. And to differentiate the second term, I'm going to think of this as a multiplied by r squared minus a squared to the power of minus a half. In other words, I'm going to use the product rule together with the chain rule for powers. So what we're going to get when we calculate this derivative here, from the first term we're going to get 0. From the second term, using the product rule, we're going to have minus 4. That is our constant here. The derivative of a with respect to a is 1, so we just get minus 4. And this will be multiplied by this term on the bottom, so I can just write that as minus 4 over the square root of r squared minus a squared. For the second term, when I use my product rule, I'm going to get minus 4a multiplied by the derivative with respect to a of r squared minus a squared all to the power of minus a half. And just as on the first slide we can use the chain rule for powers to calculate this, and I'm just going to write out what the answer is. I'll leave it for you as an exercise to check. So we get minus 4 over the square root of r squared minus a squared from the first term. And from the second term, we are going to get another minus sign left. There are going to be 2 more minus signs when we do the calculation. We have an a from this term here, another a when we differentiate what's inside the brackets. We're going to get 2 minus signs which will end up cancelling. So I'm going to get minus 4a squared, and the r squared minus a squared to the minus a half is going to be replaced by r squared minus a squared to the power of 3 halves on the bottom. And the important thing to notice is that this term is negative. This term is also negative. So therefore, we see that the second derivative that we are calculating is negative. if it is negative, this means that it will be negative for all values of a. We can see that here. It will clearly be negative when a is equal to the square root of r squared minus a squared. So we are going to have a maximum. So we have seen on the previous slide that we have a stationary point. The first derivative of the perimeter with respect to a vanishes when a is equal to the square root of r squared minus a squared. We've now seen that at that value, and actually in this case very generally, the second derivative is negative, and if the second derivative is negative, where the first derivative vanishes, we have a maximum. So what I'd like to do on the next slide is to draw our diagram to remind us of what the result is, and also to work out what this maximal perimeter is. So I've drawn again our diagram of a circle of radius r, and I've now inscribed in it a square, and the square has got perimeter of the square is equal to 4a plus 4a, so it is 8a. So this across here is 2a, this across here is 2a, up here is 2a, up here is 2a. So we now want to express this maximal perimeter in terms of the radius. And to do that, I'm going to draw a dotted line from the origin up to this point, which has coordinates a. And clearly the length of the dotted line here is the radius of our circle, and the height here is a, this distance here is a, this is an isosceles right-angled triangle, so therefore from a little bit of geometry, Pythagoras' theorem, we see that a squared plus a squared is equal to r squared. So from Pythagoras' theorem, Pythagoras, a squared plus a squared is equal to r squared. So 2a squared is equal to r squared. A and r are lengths, they are clearly positive. So this therefore tells us that a is equal to r divided by the square root of 2. So therefore the maximal perimeter of a rectangle inscribed in a circle is the perimeter of this square. It is 8 times a. A we have seen is r divided by the square root of 2. So it is 8r over root 2. And 8 is 4 times 2. 2 divided by root 2 is root 2. So we have 4 root 2 times r. And that is our final result for the maximal perimeter of any rectangle which can be inscribed in a circle. So the example of this video has been a case of looking at how we can model a problem and obtain a maximum value. There are similar problems which you can obtain a minimum value for using calculus, and one of the things that is absolutely essential to solving this problem, I think, is to draw the diagram, and that was the first thing we did, and I would always suggest that you try to do that for any problem where drawing a diagram might be helpful. So with that, I'll stop this video.